In this video, I'm going to continue to go over. I'm going to finish 5.8 moment generated functions. So let me cover the section using my lecture note. Okay. So the last time we saw the property of the moment generated functions, right? So okay. So property of the moment generated functions. The first property is this. The moment generated function of x plus a, here a is the real number, then that is equal to e to the a times t, and e to the at times the moment generated function of x. And next one is a moment generated function of ax, that is equal to moment generated function of at. Okay, so the next one, if x1 through xn through xn are independent random variables, and then with the moment generated function mx1 through mxn, then the linear combination of the random variable x1 through xn, its moment generated function going to be the product of the moment generated function of x1 through xn. Okay, so I need the schema. This is really cool. And then next one. So and then we prove it, because it's not a big deal, right? Because the definition of moment generated function is the expected value of exponential e to the x, right? So the uh, the uh, the expected value definition expected value is the integral. The integral satisfies the linear property, right? Also, since the x1 through xn are independent, say that here x1 through xn are independent, so that also, and the explain e to the t times the x1 linear combination of xi can be broken up, can be separated, I mean. So we can that multiple integral can be completely separated, so that, and then as the product of the integrals, the integral of each a random variable x1, x2, x3 through the xn. So that's why the moment generated function of linear combination of the xi is product of moment generated function of xi. Okay, so now next one, excuse me. Next one is this. Okay, so let's see. Oh yeah. So next one is the example 5.32. So okay. So distribution of a sum of Poisson random variable. Okay, suppose that the x1 and x2 are two independent Poisson random variables. So usually, but I know random variables with parameters, right, lambda and t. But let's review what Poisson random variable, Poisson random distribution is. So in the Poisson distribution, the random variable of x is the number of successes in an interval t. Okay, so certain the time interval, or certain the finite interval. Okay, we want to figure out the probability of the number of successes. Okay, so random variable x, which is the number of successes. So lambda is the average number of successes per sub-intervals. The probability of more than one event in a sub-interval tend to 0. And so we also pretty much the probability, the we're gonna the getting the one, and this at most one event in a sub-interval is the likely happen. Okay, and then probability of one event in a subuniverse 10 to lambda times delta t. So the delta t, that's the length of subuniverse, subtime universe. Okay, lambda is the average number of successes. Okay, so the event in each subuniverse is independent of other subuniverse. Okay, so now then, so the in these problems, we're gonna consider the multiple Poisson random variable. I mean, two Poisson random variables with the parameter lambda 1, lambda 2. And then the question is this: determine the probability of distribution of y is equal to x1 plus x2. Okay, so the moment general function of Poisson random variable with parameter lambda is this. So this is given. So moment general function of Poisson random variable with parameter lambda is this: e to the lambda times e to the t minus 1. Okay, so we'll just abstract that. Okay, this is given problem. So the moment general function of x1, x2 going to be, as you can see that, you see, give me a second. Yeah, so mx1 is e to the lambda 1 times e to the t minus 1, and then mx2 of t is e to the lambda 2 times e to the t minus 1. Okay, so now then, since y is what the sum of x1 x2, so we know that what the moment general function of linear combination of what random variables is going to be product of the what moment general function of random variables xi, right? So, and then the problem says that what x1 x2 are independent. You see, let me say it again. The problem says that the two Poisson random variables are independent. Can you see that right here? Oops, sorry, here, independent. Okay, so that we can use what this property. See, the property number 3. So we can use that property number 3. So okay, right here. So that my going to be product of m of x1, m x2. Which means that e to the lambda 1 times e to the t minus 1 times e to the lambda 2 times e to the t minus 1. So e to the lambda, then we can combine these two exponentials because they have same base. So we're going to get this. So which is recognized as the moment general function of Poisson random variable with lambda 1 plus lambda 2. It makes sense, right? So now thus the sum of two independent Poisson random variable with lambda 1 and lambda 2 is a Poisson random variable with lambda 1 plus lambda 2. Okay, but here's the assumption: two Poisson random variables x1 and x2 are independent. Okay, so that's the 5.8, the last example of 5.8. Okay, so I just look at the homework problems in chapter 5. I think uh, all problems are I think you can handle most all the problems without any difficulty. So let me move to chapter 6. So give me a second. So in chapter 6, I'm going to cover just 6.1. Okay, so chapter 6 is about the descriptive statistic. So yeah, so we statistic is consist of the two statistics, descriptive statistic and the inferential statistic or statistical inferences. So, but what are they? So the second. Yeah, so descriptive statistic. So from chapter 6, we're gonna learn the statistic. Okay, the chapter pretty much chapter 3, 4, 5 are those chapters are about the chapter 2 through the 5 were about the probability. So we just done, and then from chapter 6, 7, 8, 9, I think 10 are about the statistics. So This descriptive statistic is about the visualizing, organizing, summarizing data. Okay, so visualize, the histogram and bar graph and a pie chart, dot plot, okay, stem leaf plot, something like this. Okay, so then the organizing and the summarizing. So the I just assigned the reading homework, chapter 6, 6.2 through 6 point, I think the end of section in chapter 6. Okay, so you work that assignment. Okay, so those assignment about the reading. Okay, so pretty much you read and then to solve a couple of problems for each sections. All right, so, but I'll just cover 6.1 and then we move to the chapter 7. From chapter 7, we're going to learn the inference statistic. This is about estimating population parameters, and then the estimating population parameter means the uh, mean and standard deviation, variance, things like this. Okay, and then the also we're going to learn the chapter 8. We'll learn the hypothesis, okay, statistic. So we'll talk about later. So let's see. Okay, so first one, sample. We're gonna let's see. So in chapter 6.1, I'm gonna introduce many terminologies used very often in statistic. Okay, first one, sample mean, x bar. So if the n observations in a sample are denoted by x1 through xn, so x1 through xn are the you can say sample data. Okay, so or just the observations. Okay, the sample mean gonna be sum of all the observations, or you can say sample data divided by number of observation or number of data in the sample. Okay, so it's not a big deal. We use in this one in real life, right? So now, example 6.1. So physical interpretation of the sample mean as a measure of location is shown in the dot diagram of the pull-off force data. So give me a second. So we see example 6.1. I think we have to look at the figure in example 6.1 in textbook. So give me a second. All right, so see here's here's a 6.1 example 6.1. So let's consider the 8 observations on pull-off force collected from the prototype engine connectors. Okay, that example was introduced in chapter 1. The 8 observations are x1 through the x8 are given. Okay, so these are sample data. Okay, so the group set of these observations are called the sample. Okay, so now then we find our sample mean. Okay, so sum all of the sample data divided by number of sample data, so which is 13. So what's the meaning of this one? Physical meaning of the 13, that number is the let's see, measurable location. I mean, this shown in dot diagram, pull up data. See, 13 can be thought of as a balance point. Okay, so see here, 13 here. So this is a balance point. Okay, so this physical meaning of these problems. Now, next one. See, move to the up here. Okay, so now. All right, now the conceptual or hypothetical population. So the set of all observations that will be manufactured, it means it does not physically exist. So what that means, so yeah, conceptual hypothetical population. So the what the reason that we I mean the population is this what the set of all the observations, but the it's hard to figure it out. So for example, think about this. If you want to figure out the the mean of man's height in the US, and then we have to the what we have to figure out the every single man's height in the US. But the practically in practice is really difficult. It almost impossible. So we say that this is a hypothetical population or a concentric population. So population is the set of all the observations. Okay, so but the sample is just small group. Okay, subset of the population. Now the E of x mu. This is the population mean. Okay, and the capital letter N, that's the number of observations in the population. But I told you, the counting all of the observations is not possible. So let me see. Okay, so xi times f of x. F of xi is a PMF, probability mass functions. Okay, so but you see, what's the difference between the formula of the sample mean and then the formula of the population mean? PMF, right? So here, where's PMF? Actually, PMF is 1 over n. We assume that each observations will be occurred equally likely. So that means that 1 over n gonna be what? The probability of each the possible value of random variable. Okay, observations, I mean. You see? So for a finite population with n equally likely value, the PMF gonna be 1 over n. You see? All right. So now then, if we apply this one into the sample mean, so that capital letter N will be replaced by lowercase n, so then we're going to get the exactly same formula as the sample mean. Okay, so now sample mean x bar is a reasonable estimate of the population mean mu. Yeah, it makes sense. Now next one, sample variance and standard deviation. If x1 through xn is a sample of n observations, the sample variance is this, xi minus x bar. I mean, this is the difference between the observation, or we can say sample data, and the sample mean, and square, and the sum of this one, the perfect square, divided by n minus 1. So that's the formula of the variance. So yeah, it's a little bit makes sense. We're gonna sample variance. We're gonna measure the how spread out the data is spread out from the mean, right? So to measure that, we have to measure each for each observations. We have to measure the how far away from the mean, you know, for each observation. Okay, so that's the xi minus x bar. But some of them gonna be 0 because because that's the how the mean was calculated. So to prevent to get 0 as a result, as a conclusion, we take a square. Okay, now the divide by n minus, we're taking, why do we take in square? Because taking square, all the negative number becomes a positive, right? So xi minus x bar square and the sum of, I mean, xi minus x bar square makes sense, and divide by n minus 1. Here's a question, why we have to divide by not n, but n minus 1, right? So this one, yeah, before, yeah, here's um, we can answer for that question in 3 different ways, but I'm gonna introduce just one and for one of them. Okay, so before going figuring out the answer, so let's see example 6.2. Okay, so see. Let me see. All right, so example 6.2, sample variance. All right, so okay, just 30.6.1. Okay, display the quantity needed for calculating the sample variance and sample standard deviation for the pull-off force data. So table 6. Here, I think this one. Give me a second. Let me click it. Yeah, say table 6.1 right there. Okay, you see, as you can see that in table give us information about I minus x bar and the xi minus x bar square, right? So back to here. Now, yeah, right here. Okay. So now these data are plotted in figure 6.2. You see right there. So as you can see that x1, I mean, for example, give me a second. Yeah, x1 minus x bar, you see? Use x1 here, minus x bar, that will give you the distance between the x1 and x bar. So that's the measurement of the, you see, measurement, how the far away, how much, how far away from the x bar, okay? So from here, you see, this figure show us the, what, you see variability through the deviation, right? So now x squared, we find the sample variance. Okay, so the x squared going to be 1.6 over a minus 1. What is it? 1.6? 1.6 is sum of xi minus x bar squared. So you can, using the table right there, we take a sum of these numbers. Then we're going to get a 1.6 divided by number of observation minus 1, which is 7. Okay, and the central standard deviation going to be 0.48 because central standard deviation is square root of central variance, right? Okay, now then, all right. So now, okay. So let's find out. Then now we're going to study the short expression of the formula of the sample variance. Okay. So more efficient computation formula for the sample variance. So the formula, the original formula of the sample variance was this, right? Now we're gonna FOIL xi minus x bar square. Then let's see this one, right? Okay. So now then we're gonna apply the sigma each terms. Okay. So sigma xi square right there, and then sigma what, the x bar square. But since x bar square is not involved the what I, okay, moving index I, so sigma x bar square is going to be n times x bar. So we got n times x bar right there. The minus 2xi, and then I mean x bar times, I mean sigma of minus 2xi x bar. Since minus 2 x bar can be considered as a constant, so we bring it out. The sigma of xi going to be this right there, and then minus 2 x bar. Okay, so next one. And then now what? So here, the see now we gonna express this one and I mean what this one. Give me a second. This one here, and then the here. You see x bar right there. So we want to express x bar as the 1 over n times sigma xi. Well, that's the definition of x bar, right? So substituting 1 over n times sigma xi into x bar square and x bar. So we're gonna get this. Yeah, we'll get this. See, n times this, I'm talking about second term in the numerator. So sigma xi over n square, and then xi sigma xi square over n, right? So now, what is this? I mean, so give me a second. So now then, you see right there, we're gonna simplify these two terms, okay? Because in here, in the second terms, in the bottom, we're gonna get n squared, and then there is n. So n times 1 over n squared gonna be 1 over n. So we're gonna get the sigma xi and square over n, and minus 2 times sigma xi square over n. Combining them, we're gonna get minus sigma xi square over n, right? Okay. So now, okay. So now this one is called the shortcut method for calculating sample variance. Okay. So what's the difference here? I mean, what's the pros? Okay, what's the benefit of this formula than this one? So here, in the original formula of the sample variance, x bar is involved. So to figure out this, to use this formula to figure out the sample variance, we need to figure out X bar first, right? But here, in the shortcut method, X bar is not involved. So we don't have to figure out X bar first to figure out the sample variance. That's what this is shortcut method for calculating sample variance, okay? So, excuse me. So look at the example 6.3 by yourself, okay? It's really straightforward, okay? So try to look at this one by yourself. And then population variance, yeah, so same formula, I mean, pretty much similar to the sample variance formula of the sample variance, but instead of the X bar and lowercase n, we put the population mean, mu, and then the number of the observation in population, capital letter N. Okay. Excuse me. So now, here's note. So sample variance is an estimate of sigma square. Okay, and then we discuss estimation of parameters more formula in chapter 7. Yeah, in chapter 7, we want to approximate the population, the parameters. Okay, so here estimation is nothing but approximation in math. Okay, so in chapter 7 we'll study deeply how to find out how to approximate population parameters. Okay, so and then y n minus 1 is s squared. So okay, so yeah, you just pretty much read that answer. But okay, let's see together. So if you knew the true value of the population mean mu, then we could find s squared as like this, right? Okay. So now, in practice, but the value of mu is almost never known. Yeah, I told you, because this is the number of observation. The population is really huge, and then yeah, it's almost impossible to uh, collect every single data in the population. So now, and so the sum of the squared deviations about the X bar must be used instead. So what that means here, think about this. Yeah, so, a second. So now, look at this. Let's say this is population right there. So we, using the sampling method, okay? So we'll talk about sampling method later, okay? So maybe, yeah, and then we also learned the sampling method in the last semester, right? Anyway, so we collect the observation sample data. Okay, let's say this is the set of the sample data right there, right? Okay, now then, so right there, instead of mu, we want to use X bar, okay? And then the right, X bar right there. But look at this. So the, but since X bar is calculated by the sum of all the observation sample data divided by n, then definitely the one of the sample data is really close to X bar, so that Xi minus X bar is almost 0, so that we can ignore. Okay, that's why. See, so that's why. Let's say with Xk, let's say X, for example, Xk is really close to X bar. Okay, then Xk minus X bar is going to be almost 0, right? So we can ignore the Xk. Then number of the observations will be reduced by n minus 1. Okay, so now we'll see. So however, the sample observations xi tend to be closer to x bar than mu, right? Why? Because mu, the possibility mu is out of the that sample. Okay. So now, so therefore, the compensate for this, we use n minus 1 as the divisor rather than n. Okay. So keep in mind this. That's the one of the answer. So that's the all of the chapter 6. Okay. So next time I'll cover. I'm gonna start to covering chapter 7. All right. So that's for today.